Well, we've got this idea that we've got an overall heat transfer coefficient, but the actual temperature difference that's driving heat transfer is a part of that equation I kind of glossed over, right? So could we calculate the rate of heat transfer between the two fluids? Well, if we think about just one fluid and we know the entering and exiting temperature of that fluid and we know the mass flow rate of that fluid, we could calculate the rate at which the hot fluid, for example, is losing heat. That's no big deal. We just need the mass flow rate times the heat capacity of that fluid times the temperature change from inlet to exit. And we can do the same thing on the cold side, right? I mean, if you know the exiting temperature and you know how much energy has to be added or removed, that's what heat capacity tells you, and you know how much mass is going through per unit time, you can calculate the heat transfer rate. But that's not really what we were talking about before, right? We were talking about calculating the heat transfer rate based on the temperature difference between the hot and the cold side, not the temperature change across the heat exchanger. These are two different things. Now, let me pause for a second on that thought and mention that the mass flow rate times the heat capacity appear together so often as a product that we define a new term here called the capacity rate, C sub H. So C sub pH is the heat capacity at constant pressure of the hot fluid, M dot H is the mass flow rate of the hot fluid, and C sub H is the product of those two. It's the capacity rate on the hot side. Similarly, there's a capacity rate on the cold side. So the subscripts H stand for hot side, the subscripts C stand for cold side. But back to what I was saying about the difference in temperature between the hot and the cold streams. What can we do there? Well, we've simplified our equations for the two streams with the capacity rate, but we really want to know how we can calculate the heat transfer rate just given the temperature of the hot and the cold stream. Well, if you think about it, let's think of a counterflow heat exchanger. As the hot fluid goes through, its temperature goes down. As the cold fluid goes through, its temperature goes up. So what temperature difference are we talking about? Because really the temperature difference is going to vary depending on what particular position along the length of the heat exchanger you look at. So we need some mean or some average temperature for this equation to make any sense. So that's what we mean here by delta T sub M, the mean temperature. And the question is, what mean temperature should we use? What does that look like? What do we use for this average temperature difference, since the temperature difference is varying along the entire length of the heat exchanger? Well, this is where we finally find the log mean temperature difference method. Now, if you have a co-current flow heat exchanger, I know I'm flipping the direction around on you, but if you have this, it's actually pretty easy to calculate new temperatures as the two fluids move along the length of the heat exchanger, and to actually integrate along the entire length of the heat exchanger, because your heat transfer rate is going to go down as you go to the right. So you can actually derive an equation for the heat transfer rate as a function of the temperature difference at either end of the heat exchanger, the overall heat transfer coefficient, and so on. If you want to see the derivation, it's on page 717. Help yourself. Here's what you need to know. The so-called average temperature that we need is something that's called the log mean temperature difference. That's where LMTD comes from, log mean temperature difference. And the way you calculate the log mean temperature difference is with something called the approach temperatures. The approach temperatures are the temperature differences at either end of the heat exchanger. So look at the upper figure on the right. You'll see delta T1. That's one approach temperature. On the right-hand side of that heat exchanger, you see delta T2. That's the other approach temperature. And so since the upper figure is a co-current flow or parallel flow heat exchanger, you'll notice that the hot and the cold stream come in on the left and exit on the right. Now, delta T1 versus delta T2, you could actually flip them around, it turns out, and won't make a bit of difference. So in the log mean temperature difference equation, it doesn't matter which side you call the delta T1 or the delta T2. You just need the approach temperatures on either side. Because if you flip the definition in the numerator, you'll flip it in the denominator, you're basically introducing a sign difference in both the numerator and denominator, and it cancels. Now, it turns out that this log mean temperature difference also works just fine for countercurrent flow. So you still need the approach temperatures, and even though the cold stream is going one way and the hot stream is going the other, as a matter of fact, the approach temperatures are still the differences on either end of the heat exchanger, and this will still work just fine. Now there are cases where you could transfer heat with a fluid and the temperature of that fluid won't change at all. And that may seem strange at first, but remember, fluids can change phase. So if you've got a liquid, it can boil. If you have a gas, it can condense. And so if we have, let's take the upper figure for example, if we have a condensing fluid, a fluid that is hot, but it's going from the vapor phase into the liquid phase, then its temperature will remain constant throughout the entire length of the heat exchanger, as long as the pressure remains constant, which is good, which is reasonable to a good approximation. And so the condensing fluid temperature will never change. So what do you do then? Because now our temperature difference is, you know, we have to throw out the window what we just had a minute ago. Well, in that case, number one, the heat transfer rate of just the condensing fluid itself is no longer a capacity rate times the temperature change. On the cold side it is, because the cold side is increasing its temperature. So it has a different temperature at the inlet as it has at the exit. And the equation we had before still applies. But on the hot side, we have to account for the phase change with the latent heat of vaporization. So you see the HFG on the hot side? Well, that's what we're using to calculate the heat transfer rate coming out of the hot fluid. Similar argument for a hot fluid where we have a cold fluid that is boiling. If the cold fluid is boiling, it's going from the liquid phase to the gas phase, and it will do so at constant temperature, assuming again that the pressure on the cold side remains relatively constant. But we will still use the latent heat of vaporization on the cold side to calculate the rate of heat transfer going into the cold fluid. Did you notice that that derivation was performed for a simple single pass shell and tube heat exchanger, or what's also called a sidearm heat exchanger? What happens when we have a real heat exchanger? What if there's cross flow? What if there are multiple shell passes or multiple tube passes? Then what happens? Well, then we have to correct the log mean temperature difference. So we actually have some charts. They're in your text. You should bookmark this page. It deserves a tab. This is where you will get your correction factors labeled F on the y-axis. The first thing you have to do is select the appropriate configuration of heat exchanger that you're actually working with. Then you calculate the log mean temperature difference as if it were just a simple single pass shell and tube heat exchanger, and then use the correction factor from the chart to correct that log mean temperature difference. So you'll have to locate the correct point on the x-axis and then locate the appropriate curve, but you see equations in each of these where lowercase t's represent the tube side and uppercase t's represent the shell side. I'll work an example for you so you can see how this works, but basically the parameter p tells you where you're at on the x-axis and the parameter r tells you which curve to read off. You intersect those points, or you intersect those two to a point and go over to the left to read the correction factor F. So then, instead of just using the log mean temperature difference itself, you multiply it by the correction factor and then plug that into the equation. Now, one thing that's important is it turns out that this parameter R actually has some meaning. It's actually the capacity rate on the tube side divided by the capacity rate on the shell side. And so what that means is the capacity rate can actually vary from 0 to infinity. Now, if the capacity rate goes to infinity, then the correction factor goes to 1. Now, how can it go to infinity? What does that mean? Well, that means that we have an infinite capacity rate on the tube side. What does that mean? Well, that means that we can put as much energy into the fluid on the tube side as we want, and it will never change its temperature. Well, how is that possible? Well, that's possible if on the tube side we have either a boiling or a condensing process. Okay, now of course we could be taking energy out of the tube side also, so that's why I said putting energy in or taking it out. So in that case, we basically have an infinite capacity rate on the tube side, and R goes to infinity. Now that's not really what's going on physically in the real world, because there's no fluid that you can add thermal energy to and it doesn't change its temperature, except when it's doing a phase change, right? If there is a phase change on either the tube side or the shell side, you will end up with R equal to either 0 or infinity, and that is the most effective heat exchanger that you can have. And so the correction factor F simply goes to 1. So I said all that to say this. Make a note on this page that says if you have boiling or condensing in the heat exchanger, then the correction factor F is equal to 1. And there's probably a note somewhere in the text that says that. Maybe you want to highlight it. But certainly you need to add it so you know what to do if I give you a heat exchanger that has either boiling or condensing on either side. So how do we finally use this log mean temperature difference method? Well, remember, what we're trying to do is select a heat exchanger. We know what the incoming stream temperatures are. We know what we want the exiting stream temperatures to be. Plug it all into the log mean temperature difference method. We know what heat transfer rate we want, so we can solve for the UA product, or more particularly, we can solve for the amount of area required in the heat exchanger in order to accomplish the desired heat transfer rate Q dot with the desired temperature change that's represented in the delta T log mean term. So the more, the higher temperature change we want, the more area we're going to need, the higher the heat transfer rate desired, the more area we're going to need, and we just have to select a heat exchanger that has at least, well, preferably more area than what we've calculated here. Now, why would we want a heat exchanger with more area? Well, the heat exchanger is probably going to foul, and we probably don't want to have to take it apart every day just to remove a little bit of fouling. We'd like to be able to let a little bit of fouling, or a decent amount of fouling build up, and yet the heat exchanger still work, so we can increase the amount of time required between servicing to some reasonable period. So a little bit of excess or over surface percentage is actually very beneficial when you design a heat exchanger. Now, it's going to cost a little more, but you have to trade off the extra cost with the lower cost of maintenance.